Our reality could be a three-dimensional shadow, a shadow of something deeper. That's the frontier now, in physics, this profound search for hidden dimensions. It's a quest that could rewrite the laws of the universe, because dimensions beyond our sight might bend the rules of gravity. That's why our most powerful machines are hunting. They're listening for echoes from these unseen realms. How much of the true cosmos is just hiding in plain sight? The idea of hidden realms isn't new. It has a long history, a path that leads right to the questions we're asking now. There's this world with only two dimensions, a flat sheet of existence. The beings there are simple shapes. They can move left and right, forward and back, but up is a concept that means nothing to them. That was the world of Flatland. A thought experiment from 1884 by Edwin Abbott. In it, a three-dimensional sphere visits this flat plane, and to the squares and triangles living there, the sphere doesn't look like a ball. It appears as a circle that changes size mysteriously. They have no framework for it, no language. They are prisoners of their own perception. And that's the point of the allegory. We, in our three-dimensional world, might be just as blind. If a four-dimensional shape passed through our space, we'd only see a three-dimensional slice of it. An object morphing in ways that seem to break our physics. Flatland was more than a clever story. It was a warning about the limits of intuition. It asked us to consider that our reality might just be a fragment, a piece of a much larger and stranger truth. But that philosophical seed needed a mathematical framework. For centuries, science had three clear dimensions of space. And time was separate, a universal clock ticking in the background. Then came Albert Einstein. His theory of relativity did something revolutionary. It wove space and time together into a single fabric called spacetime. That was the fourth dimension, not a spatial direction you could point to, but part of the universe's geometry. A massive object like the sun doesn't just sit in space, it warps this four-dimensional fabric, and we perceive that warping as gravity. That was the crucial leap. Dimensions were no longer just empty stages, they were active participants. They could bend and stretch, they could interact with the energy within them. Einstein's work showed that to understand the cosmos, you had to abandon the comfortable, separate boxes of space and time. You had to embrace a more complex reality. One that was interwoven, that set the stage for everything that followed. If we could accept time as a dimension, what was stopping us from asking about a fifth? Or a sixth? The journey moved from speculative fiction into the hard language of mathematics, where the next great mystery was waiting. Einstein's spacetime was a four-dimensional fabric. But for some physicists, it felt incomplete. The equations for the cosmos had a hole, a place where gravity and the quantum world just wouldn't meet. Then there was this radical proposal. What if the most fundamental things weren't tiny points, but these unimaginably small, vibrating strings? That was string theory. It promised a single framework, an elegant one, to explain everything, but there was a catch, a profound one, unavoidable. For the math of string theory to hold together, for the equations to balance without collapsing, the strings couldn't just vibrate in our three dimensions of space and one of time. The numbers demanded more room. They required 10 dimensions. Later versions even pointed to 11. This wasn't a speculative add-on. It was non-negotiable. For the theory's internal logic, the universe by this math had to be built with extra spatial dimensions. They weren't optional, they were essential. So where are they? Why don't we see them? The leading idea is compactification. Think of a single strand of hair. From a distance, it looks like a one-dimensional line. But bring a powerful microscope right up to its surface, and you see it has this rich circular structure, wrapped tightly around its length. To a tiny ant walking on that hair, that circle is a whole new dimension to explore. In string theory, 6 or 7 of the extra dimensions are thought to be curled up like that, but on a scale so phenomenally small, billions of times smaller than an atomic nucleus. Completely hidden from our everyday perception, even from our most powerful particle colliders, they're woven into the fabric of reality but folded away. This mathematical necessity changed the whole conversation. The search for hidden dimensions wasn't just a thought experiment anymore, not just something from Flatland. It was now a concrete prediction, a quantitative one from our most ambitious attempt at a theory of everything, and it offered this vision of reality. A breathtakingly beautiful one. In this view, every particle we know, every force, the electron, the photon, even the gravitational pull of a planet, it's not a fundamental object. It's just a different note, a specific vibrational pattern of these tiny, higher dimensional strings. The diversity of the cosmos is a symphony, a complex harmony. Played out in a hidden, multidimensional space, we only hear the music without seeing the grand, intricate instrument it's played on. String theory wasn't the first to suggest something like this. There was a mathematician, Theodore Kaluza. He wrote a letter to Einstein. In it, he had this astonishing idea. Kaluza took Einstein's own equations, the ones for gravity, describing 4-dimensional spacetime. And he did something very simple. He added a 5th dimension, just one more. He didn't alter the math, he just extended it. And when he solved these new 5-dimensional equations, something happened. The equations for gravity were still there, but alongside them, perfectly described, were the equations for another force: electromagnetism, light, electricity, magnetism. In Kaluza's math, the two great forces of the time weren't separate. They were woven together, different expressions of a single geometry in a higher dimensional space. Gravity was the bending of the 4 dimensions we know, and electromagnetism, that was the ripple in the hidden 5th dimension. Einstein was stunned. He called the idea exceedingly impressive, but there was a big question. Where was this 5th dimension? Why couldn't we see it? A few years later, a physicist named Klein offered an answer. He said the dimension wasn't missing, it was just incredibly small, curled into a circle so tiny, 1 billion times smaller than an atomic nucleus, that it was invisible to us. Any particle moving through this coiled dimension would have its motion quantized. It could only exist in specific, discrete states, and from our 3-dimensional perspective, those different states would look like different particles. Particles with different electric charges. This was the Kaluza-Klein theory, a beautiful, daring vision. It ultimately couldn't explain all the forces we later found. Like the strong and weak nuclear forces, so it was set aside, but its legacy was profound. It was the first concrete, mathematical demonstration. It showed that hidden dimensions could be more than a philosophical puzzle. They could be a unifying principle, a way to simplify the cosmos, to show that what we perceive as separate, fundamental rules might just be shadows. Different angles of a single, multidimensional truth. That seed of an idea never died. It just waited for a new generation to pick it up and ask, what if there are more than 5? A beautiful idea isn't enough. It has to make predictions. It has to leave marks on the world we can actually see. And that's the real challenge for these hidden realms. If they're curled up, smaller than anything we can probe, how could they affect us? The answer might be in gravity itself, because gravity in our universe is weak. It's perplexingly weak. Think about a tiny refrigerator magnet lifting a paperclip. That magnet's electromagnetic force is fighting the gravitational pull of the entire planet. And it wins. Gravity is feeble. It's feeble beyond explanation, unless its true strength is being diluted. Imagine a garden hose. Water flows through it with a certain force. Now poke many tiny holes along its length. The water leaks out in all directions. From inside the hose, the flow along the main channel seems weaker. The strength hasn't vanished, it's just spread out. That's the core of the idea. What if gravity isn't confined to our three-dimensional brain? What if it can leak? It can seep into the extra, compact dimensions. Its influence would spread thin across a higher dimensional volume, and from our vantage point, trapped in our three-dimensional slice, gravity would appear as a faint whisper. A ghost of its true power. This concept resolves an old puzzle. It suggests we're not seeing gravity in its full, multidimensional glory. We're only sensing the tiny fraction stuck to our familiar world. The rest is echoing in realms we can't access, so the search becomes a hunt for echoes. If gravity is interacting with hidden dimensions, there should be consequences. Subtle deviations in its behavior, especially at incredibly small scales. Experiments are now trying to measure gravity between objects placed a hair's width apart. They're looking for a telltale sign, a moment where the force strengthens just slightly, as the distances become so tiny that the probe begins to feel the full, undiluted grip of gravity from the extra dimensions. It's a whisper we're straining to hear, a signature written in the weakest force we know. String theory had a problem, a deep one. Researchers found not one version but five. Five distinct, mathematically consistent sets of rules, all claiming to be the fundamental description of reality. It was a landscape, a confusing one. If this was the theory of everything, why were there five? It was a crisis. Then, in the 90s, Edward Witten proposed a synthesis, M-theory. The M stands for many things. Membrane, magic, mystery. The idea was that the five string theories weren't rivals. They were different faces of a single, deeper truth, like different maps of the same continent. But for this to work, the math demanded something new. Not 10 dimensions, but 11. A single framework needed one more spatial dimension to tie it all together. And with that 11th dimension came a new character, the Brane, short for membrane. In M-theory, the fundamental objects aren't just one-dimensional strings. They can be points, sheets, higher dimensional volumes. Our entire universe, with its three spatial dimensions, could be one such object, a three-brane. A vast floating island, and it might not be alone. It could be drifting in a larger space, a higher dimensional arena called the bulk. In this picture, we aren't just blind to extra dimensions. We might be trapped on one. All the particles and forces we know, except possibly one, could be stuck to the surface of our brain, like ink on a page. They cannot leave, they define our reality, but gravity might be different, the geometry of spacetime itself. It might be the only force that isn't confined. It could be free to spread, to seep out into the surrounding bulk. This offers a new answer to gravity's weakness. Its strength isn't diluted by leaking into tiny, curled-up dimensions. Instead, it's spilling out into a vast, unseen ocean. We only feel the tiny puddle that remains on our island. The braneworld concept transforms the search. It turns it from a microscopic hunt into a cosmic one. If our universe is a brane, then the bulk is out there, a realm of ultimate elsewhere, and collisions or ripples in that bulk could have left scars on our cosmos. Imprints from dimensions we cannot touch, written across the sky. There's this beautiful, dizzying puzzle. If the extra dimensions are curled up, what shape do they take? It can't be a simple circle. For string theory to give us the particles and forces we see, the geometry has to be exquisitely complex. The leading candidates are these objects, Calabi-Yau manifolds. Six-dimensional shapes, and by their nature, they're almost impossible to visualize. Their surfaces twist and fold in intricate patterns. They have holes, tunnels of various dimensions. They're like the hidden engines of reality. In the theory, the way a string vibrates isn't just about its tension. It's about the space it's moving through. A guitar string plays different notes depending on the length and shape of the guitar's body. A fundamental string works the same way. Its vibrational note, whether it becomes an electron, a quark, a photon. That's determined by the exact geometry of the Calabi-Yau manifold it's wrapped within. The shape of these unseen, microscopic dimensions dictates everything: the number of particle generations, the strengths of the forces, even the existence of matter itself. So the implication is staggering. The entire rulebook of our universe, the laws we've spent centuries uncovering, they might not be fundamental laws at all. They might be local bylaws, a direct consequence of which particular Calabi-Yau shape got chosen when our cosmic bubble formed. This idea is called the landscape. It suggests there could be a vast number of possible stable configurations, maybe 10 to the 500, each with its own unique set of physical constants and laws. In that view, our universe, with its specific particles and forces, is just one possibility, one page in a near-infinite cosmic catalog. The compactification of dimensions isn't just a neat trick to hide them. It's the very mechanism that sculpts reality from pure geometry. We are living in the echo of a shape we cannot see. But these extra dimensions, if they're real, they have to leave some kind of mark. They can't hide completely, so where do you look? You look for cracks in the laws we think we know, and the first place to search is gravity itself. Gravity is the universal force. It might be the one force that's free to wander into the bulk, and if it does, its strength should change with distance. In our familiar world, from planets to apples falling, gravity follows an inverse square law. You double the distance, the pull weakens by a factor of 4. That's a cornerstone, but what if, at incredibly small scales, that law starts to break? Imagine 2 specks of dust brought closer than the width of a human hair. In a universe with large extra dimensions, gravity at that tiny range isn't just operating in our 3-dimensional space. It can suddenly spread into the full, higher dimensional volume. Its lines of force have more directions to flow, and from our perspective, that should make the gravitational pull between those 2 specks grow stronger. Faster than the inverse square law predicts, it would be like a dam breaking. For a fleeting moment, at a microscopic distance, you'd feel gravity's true, undiluted strength. This isn't just a theoretical curiosity. It's a precise, testable prediction. Teams of scientists have built some of the most delicate machines on Earth to hunt for this effect. They use devices called torsion balances. Imagine a tiny bar suspended by an incredibly thin fiber. You bring a carefully shaped mass close to one end. The gravitational attraction should cause the bar to twist just slightly. By measuring that twist with lasers, they can map the force of gravity down to distances smaller than a millimeter. Other experiments use microscopic cantilevers like tiny diving boards, watching for a tremor as a mass passes nearby. They're listening for gravity's whisper to become a shout. A single, clear deviation from Newton's ancient law at these sub-millimeter scales would be more than a new data point. It would be a direct fingerprint. A monumental imprint left by a hidden dimension. It would tell us gravity has been keeping a secret, that it has more room to breathe than we ever imagined. And it would solve one of the most perplexing puzzles in physics, the hierarchy problem. Why is gravity so absurdly weak compared to the other forces? The answer would be stunningly simple. It isn't weak. We've just been stuck in a corner of a much larger room, feeling only the faintest echo of its true power. Gravity isn't the only signal, though. There's a second kind of imprint these hidden dimensions could leave, a much more dramatic one. It's about making something from nothing and then watching it disappear. In a universe with large extra dimensions, gravity's real strength only shows up at incredibly high energies. Energies we can't reach here on Earth unless we find a shortcut. A cosmic shortcut. The Large Hadron Collider smashes protons together almost at light speed. In our normal 3-dimensional world, that collision energy is huge, but it's still nowhere near the energy you'd need to make a black hole. That scale is called the Planck energy. It's astronomically high, but here's the thing. If gravity can spread out into extra dimensions, its fundamental strength scale could be much, much lower. Low enough that we might actually reach it. In that case, the most powerful collisions inside the LHC might do more than just create new particles. They might, for a split second, warp spacetime so severely that they pinch off a tiny piece of reality. They could make a microscopic black hole. Now, forget the science fiction idea. This wouldn't be some cosmic vacuum cleaner. It would be smaller than a proton. And based on Stephen Hawking's work, a black hole that small would be unstable. It would evaporate. In a burst of radiation, it would vanish almost as soon as it formed. That evaporation would leave a very specific mark in the detectors, a sudden, symmetric spray of many different particles, all coming from one vanishingly small point. It would look like nothing else we see in physics. For more than a decade, scientists at the LHC have been sifting through mountains of collision data, looking for that pattern. They're hunting for a ghost that, if found, would prove something astonishing. It would mean that for a split second, our machines did more than discover a new particle. They manipulated the fabric of spacetime itself. They touched a higher dimensional geometry. That search changes what these colossal rings are. Built to find the smallest pieces of matter, they become something else. They become potential gateways, instruments that might not just probe our universe but puncture it, offering a direct, violent look into the bulk, a test that could confirm in an instant that our world is a brane floating in a larger, hidden sea. Every collision is a question thrown at the void, and we are listening intently for an answer written in the decay of something that shouldn't exist. There's a third type of ghost they search for in the debris, not defined by what shows up but by what goes missing. In every collision at the Large Hadron Collider, the books have to balance. The total energy and momentum going into the smash has to equal the total coming out, recorded by the detectors around it. That's a fundamental law, conservation. But sometimes something slips the ledger. Think of a perfect bank heist. The only evidence is a locked vault door and money that's just gone. No alarms. No footprints. That's the mystery of missing transverse energy. In the data, it shows up as an imbalance. A collision happens, known particles spray out, but their combined energy doesn't add up. A significant part seems to have just disappeared. For physicists, that's not a mistake. It's a clue. One of the strongest suspects is the graviton, the hypothetical particle that carries gravity. In the braneworld picture, if our universe is a membrane, most particles are like ink stains. They're stuck to the page, but the graviton, linked to spacetime geometry, might be different. It could be the only particle that isn't confined. So in a violent collision, if a graviton were created, it might do something nothing else can. It could just leave. It could carry its energy and momentum with it, slipping off our brane and into the higher dimensional bulk. From our perspective, stuck on our three-dimensional island, that energy would vanish. It would register as a silent blank spot in the detector, a nothingness that actually screams. So the search is for these quantum-scale bank heists. Teams analyze billions of collisions. They build a painstakingly detailed map of normal particle behavior. They're looking for the statistical anomalies, the rare events where the energy books don't balance, and no known particle, no neutrino or dark matter candidate can explain the gap. It's detective work of the highest order where the clue is an absence, a void that paradoxically could be the strongest evidence yet for a realm beyond our own. It tells us that to find hidden dimensions, we might not need to see something new. We just need to notice what isn't there. The hunt for hidden dimensions isn't just for our machines. The deepest evidence might be written across the sky. You have to look back to the very start. Right after the Big Bang, the universe was unbelievably hot. Unbelievably dense. It was pure energy, a place where space and time themselves were being made. In that first furnace, the energy was so extreme that all the forces were one force. Gravity included, and if extra dimensions are real, they wouldn't have been curled up then. They would have been open, active. They would have been right there, part of everything. Their shape would have changed how the baby universe moved, which brings us to cosmic inflation, that idea that the universe blew up faster than light for a split second. It smoothed everything out. It planted the seeds for all the galaxies. What if that huge burst was started by the extra dimensions or shaped by them? Then, as the universe cooled, the forces split apart, and the extra dimensions would have curled up fast. They would have shrunk down into their tiny, stable forms. That change from an open state to our three-dimensional one would have sent waves through everything, shock waves, and those shock waves would have left marks. Permanent ones, we can still see those marks. We see them in the cosmic microwave background, that cold glow everywhere. It's the afterglow of the Big Bang. A picture of the universe at 380,000 years old. On that glow, there are tiny temperature differences, 1 part in 100,000. Those are the blueprints for all the structure we see. But in those patterns, physicists are looking for something else, specific oddities in the statistics of the fluctuations. Or special signs in the polarization of that old light, the direction its waves point. These could be fossils, direct imprints from when the extra dimensions were open and then snapped shut. They'd be whispers from a time when reality had more rooms. Finding a signature like that would be different. It wouldn't be a lab result. It wouldn't be a particle track. It would be a message from the universe itself, written in the first light, saying our three-dimensional world is just one chapter. The whole cosmos is the detector. Its oldest light is the data. The cosmos has these two huge, invisible secrets, dark matter and dark energy. They make up 95% of everything, and we know almost nothing about them. They're the great unknowns, but maybe they aren't just missing pieces in our picture. Maybe they're clues that something is missing from the picture itself. That the search for hidden dimensions could be the key. Think of dark matter first. We know it's there because galaxies spin too fast. The gravity from the stars we see isn't enough to hold them together. Something invisible provides the extra glue, but in all our searching, we've never directly caught a dark matter particle. It's frustrating. There's this radical idea from Brane world models. What if dark matter isn't in our universe at all? Not exactly. Imagine two sheets of paper floating parallel to each other in a higher dimensional space. Our universe is one sheet. All the particles we know, the light we see, are stuck to it. But another brane, a shadow universe, could float right next to ours. Separated by a microscopic gap in a hidden dimension. On that other brane, there could be a whole other set of particles, with their own forces, their own rules. They would be completely dark to us, invisible, except for gravity. Gravity might be the only force that can bridge the gap between branes. The gravity from particles on that shadow brane would leak into our space. It would pull on our stars and galaxies. To us, it would feel exactly like an invisible source of mass, a perfect explanation for dark matter that we can never touch. It's a ghost whispering to us from a parallel reality, separated by a dimension we cannot cross. Then there's dark energy, an even stranger mystery. It's the force causing the expansion of the universe to accelerate, a kind of anti-gravity woven into the fabric of empty space itself. Where does this repulsive energy come from? One possibility ties back to the shape of those hidden dimensions. Remember the Calabi-Yau manifolds, the intricate shapes that could define our physics. Over cosmic time, these shapes might not be completely static. They could be slowly evolving, uncurling just a tiny bit, or vibrating in a new way. That subtle shift in the geometry of the unseen realms would change the energy content of the vacuum of our space. From our three-dimensional perspective, it would look like a new, pervasive force pushing everything apart, So dark energy, in this view, wouldn't be a new field. It would be an echo, a cosmic sigh from dimensions settling into a new configuration, stretching the very stage we stand on. These ideas are highly speculative. They live at the very edge of theoretical physics, but that's the point. They show the search for hidden dimensions isn't some isolated, abstract puzzle. It's deeply connected to the biggest questions we have. It could be the thread that pulls everything together. The invisible 95% of the universe, the parts that currently make no sense, might be the most direct evidence we have. Evidence that we are not seeing the full story, that reality has more rooms, more layers, more dimensions than we ever dreamed. The darkness isn't empty. It might be where the truth is hiding. The deepest clues might be in the quietest places, not in a giant ring, on a tabletop, in a clean room. That's the new frontier now, this miniature revolution. For so long, testing gravity at tiny scales was just a dream. The force is so weak, any vibration, any stray charge would drown it out completely. It looked impossible. But now, physicists are treating that impossibility as an engineering problem. They're building the quietest machines on Earth, not to listen to the cosmos, but to feel its faintest tug. The goal is simple: to measure the gravitational pull between two microscopic masses, brought closer together than the width of a human hair. At these distances, microns apart, the inverse square law we know might start to falter. If gravity is leaking into extra dimensions, this is where its true strength should show itself. The pull should get stronger, a measurable deviation. That would be a direct fingerprint, a sign of a hidden realm, but to see it, you have to eliminate every other force. You need near-perfect silence. This is where nanotechnology meets quantum sensing. The experiments are marvels. One approach uses tiny oscillating cantilevers, like microscopic diving boards. A gold sphere, smaller than a grain of sand, sits on one. Another mass is brought incredibly close. The gravitational pull between them, infinitesimally small, will bend the cantilever, just a fraction of an atom's width. To see that movement, they use lasers or quantum effects in superconductors, sensors of almost unimaginable sensitivity. Other experiments use torsion balances but scaled down to a chip. They suspend a tiny bar on a fiber thinner than spider silk, watching for the slightest twist as a mass passes by. The whole setup is shielded in a vacuum. Cooled, isolated from the world's constant hum, they're creating pockets of stillness to hear gravity's whisper. And what's remarkable is many run at room temperature. They don't need the extreme cold of a quantum computer or the vast energy of a collider. That makes the search accessible, a kind of grassroots physics. University labs everywhere can contribute, each refining a different technique, chasing the same signal. It democratizes the question. The hunt for the architecture of reality isn't confined to a few mega facilities anymore. It's on lab benches, in the persistent, meticulous work of engineers and physicists, who believe if you listen closely enough and build carefully enough, the universe will reveal its secrets in the quietest of ways. While tabletop experiments are listening for gravity's quiet signature, there's another approach that just uses raw power. That's the Large Hadron Collider, deep underground, on the border of France and Switzerland. It's a machine on a completely different scale. It's a time machine and a microscope all in one. You accelerate protons to almost the speed of light and smash them together. And for a fraction of a second, you recreate the conditions that existed a trillionth of a second after the Big Bang. At that moment, the universe was this seething ocean of pure energy. Hotter and denser than the core of any star, and if extra dimensions exist, they wouldn't have been hidden then. They would have been open, active, a direct part of the physics of that primordial fire. So each collision inside the LHC's 27-kilometer ring is more than a search for new particles. It's a recreation of that ancient, multidimensional state. For a fleeting instant, as energies skyrocket, the barriers between our familiar dimensions and the hidden ones could grow thin, or even vanish. The machine becomes a probe, not just of matter, but of the architecture of space itself. You're asking the universe to briefly uncurl its hidden geometry, to show us a glimpse of its true form. The data from these collisions is staggering. Measured in petabytes, a flood of digital information that's really the debris of these miniature cosmic rebirths. And there are two massive detector collaborations, Atlas and CMS. They're the eyes of this whole endeavor, cathedral-sized instruments wrapped around the beam pipes, layered with sensors to capture every possible fragment of these explosive moments. Their teams aren't just looking for known particles like the Higgs boson. They're forensic scientists sifting through the aftermath for anomalies, for events that defy the standard model's expectations. They hunt for the exotic signatures hidden dimensions might leave behind, maybe a new heavy particle, a Kaluza-Klein resonance appearing and decaying in a specific, unexpected way. Or the sudden production of microscopic black holes that vanish in a hail of radiation. And most tellingly, they search for events with significant missing transverse energy, where momentum seems to vanish from the detector entirely, as if it were carried away by a graviton slipping into the bulk. Every one of these signatures is a potential message. A crack in reality's facade. The work is a monumental exercise in patience and precision, comparing mountains of real data against even larger mountains of simulated predictions. It's a search for a needle in a cosmic haystack where the needle might rewrite the laws of physics. Each collision is a question hurled into the heart of creation. And we've built the most complex listening devices in history, waiting for an answer. The most extreme physics happens in places we didn't build. They're the corpses of massive stars. A giant star dies in a supernova and its core collapses. It becomes a neutron star, the mass of our sun, crushed into a sphere the size of a city. A single teaspoon of that material would weigh 1 billion tons. Matter pushed to a breaking point. Gravity there is so intense it warps the rules. That's where you look for cracks. If extra dimensions change gravity, the effects wouldn't just be in a lab. They'd be magnified, screamingly obvious where gravity is king. On a neutron star, gravity is 100 billion times stronger than Earth's. The matter is a quantum soup of neutrons. Pressures so high that new states of matter might form. Our equations for this are already at the edge. But if gravity is different, if it leaks into other dimensions, those equations would be wrong. The predicted size of the star for its mass, the way heat moves through its crust, even the point it collapses into a black hole, all of it would shift. You'd see a deviation, a signature in the stars themselves. This isn't just theory now. We have a new window. The Neutron Star Interior Composition Explorer, NICER, is on the space station. It doesn't take pictures. It's a precision timing instrument. It stares at pulsars, those spinning neutron stars that sweep radiation beams like lighthouses. NICER measures the arrival time of each X-ray pulse. By tracking how the X-rays change as the star rotates, scientists can map the hotspots. They can measure the star's mass and its radius. That measurement is a fundamental test. Our models of ultra-dense matter predict a specific relationship between mass and size. If the stars we see fall outside that curve, something is missing from our physics. It could be a new state of matter, or it could be gravity itself behaving differently because of hidden dimensions. The search goes beyond single stars. It goes to their most violent dances. When two neutron stars spiral together and merge, they create the most powerful gravitational events since the Big Bang. They shake spacetime, sending out ripples we can detect with LIGO and Virgo. The shape of those gravitational waves, their frequency and how they change, encodes information. Information about the star's internal structure and how gravity works. Before they collide, tidal forces stretch each star. How much it distorts depends on the stiffness of the matter inside. That stiffness depends on the crushing force of gravity. A hidden dimension modifying gravity would alter that stiffness. It would change the tidal distortion. It would leave a fingerprint in the gravitational wave signal. We're in an era of multi-messenger astronomy now. We can see the flash of light from a merger and feel the tremors in space-time. Combining these signals gives a full picture. Any inconsistency between what the light tells us and what the gravitational waves tell us would be a glaring clue. A clue that our understanding of gravity in the most extreme conditions is incomplete. So the frontier isn't just in tunnels or on lab benches, it's out there. In the silent, rapid spin of a city-sized cinder, in the final, rippling scream of two dead stars, the universe is performing the experiments. Our job is to watch with sharper eyes and listen with more sensitive ears. To listen for the moment its behavior tells a story we haven't heard. A story written not just in particles or forces, but in the geometry of creation itself. This geometry is where math meets the cosmos. The extra dimensions in string theory, the ones curled up so small, they aren't just empty, they have a shape. A specific, exquisite shape, and the leading candidates for that shape are called Calabi-Yau manifolds. Describing them is a challenge. They're six-dimensional spaces, which means we can't picture them, not fully. But mathematicians can describe their properties with equations. Artists make visualizations, hints of their complexity. They look like intricate, multi-dimensional jewels. Surfaces that twist and fold in on themselves, woven with tunnels and holes. They're not random, they're solutions to a set of very demanding mathematical conditions. Conditions the physics needs to be consistent. In a way, they're the hidden engines, the vibrations of the fundamental strings, the ones that become every particle. They aren't free. They're constrained by the geometry they move through. Think of a violin string. The note it plays depends on the length of the string and the shape of the violin's body, the hollow chambers that resonate. A Calabi-Yau manifold is the universe's violin, the specific vibrational pattern that makes an electron, or a photon, that's determined by the exact shape of this hidden, six-dimensional space. The number of holes, the topological features, they act like a cosmic tuning board. They dictate how many ways a string can vibrate, and that number translates directly into the physics we see. It determines how many generations of fundamental particles exist. We see three: the up and down quarks, the charm and strange, the top and bottom. Why three? It could be because the particular Calabi-Yau shape for our universe has a specific topological feature, one that yields exactly three stable, low-energy vibrational patterns for the matter strings. The strengths of the forces, certain symmetries, even the fact we have more matter than antimatter, all that could be locked into the twists and tunnels of this unseen geometry. This changes how we see physical law. The constants we measure, the rules we've discovered, they might not be fundamental truths written on a cosmic tablet. They might be local bylaws, a direct consequence of which particular Calabi-Yau manifold our pocket of reality settled into as the universe cooled, so the search becomes a grand cataloging project. Mathematicians and physicists work to enumerate these possible shapes. They've found thousands. Estimates suggest a staggering landscape, maybe 10 to the 500 distinct forms. Finding the one that matches our universe is like searching for a single snowflake in a blizzard that fills the cosmos. It's a task where pure, abstract mathematics holds the key to physical possibility. The equations for the shape of hidden space are, in essence, the equations for everything we see. The universe is a geometric melody, and we're just beginning to learn how to read the sheet music. This search goes beyond science. It becomes a kind of philosophical mirror. It makes us ask a question that's been around for centuries. What is real? Everything we know about the universe comes from data. Light in telescopes, particles in detectors, the way gravity pulls on a mass. But if our senses and every tool we make are stuck in just 3 dimensions of space and time, then what are we really measuring? We're like the shapes in Flatland. We're studying shadows on the wall of a cave. We can document the shadow's behavior. We can chart its movements, predict what it will do next. But from that data alone, can we ever say we know the true object, the object that exists in a fuller space? This idea humbles us. It challenges a very human instinct. The instinct that our perspective is central, that what we can touch and see defines what's fundamental. The hidden dimensions idea suggests the opposite. The particles we call fundamental, the forces we think are elemental, might not be basic at all. They could be emergent phenomena, low-energy echoes. Vibrational shadows of something more complex, something with more dimensions. The solidity of matter, the flow of time, even the space between things, might be illusions of scale. They're comfortable approximations. They work in our limited corner of a much larger reality. This changes how we think about knowledge itself, our epistemology. If direct experience is inherently limited, then we need something else to guide us. We have to trust the language of mathematics, its internal consistency, its predictive power that becomes our compass. When equations point toward extra dimensions, they're not just suggesting new physics. They're offering a map to a territory our bodies can never visit. It asks for a leap of faith in reason, a belief that the universe isn't just lawful but elegantly so, and that the human mind, through logic and symbol, can perceive truths our senses will never show us. So the search isn't just about finding new dimensions. It's about redefining what it means to discover. It's learning to see with the mind's eye and accepting that the truest picture of reality might be one we can never directly see. But the search has this deep challenge. It's about testability. Some physicists, even ones who like other ways to unify gravity and quantum mechanics, they ask, if these extra dimensions are curled up so small we could never reach them, then what are we doing? They say a theory you can't test, even in principle, starts to leave science. It becomes metaphysics, a beautiful story, but not one we can check. That's the testability debate. It goes right to what science is. The worry is, without a clear prediction, something that could prove it wrong, the idea of hidden dimensions stays elegant speculation. Always out of reach, but the people working on these theories, they see it differently. These ideas aren't one thing. They don't make just one prediction. They give a whole range of possible signatures across totally different scales. On the small end, there are tabletop gravity experiments looking for tiny deviations. Then there are particle colliders searching for missing energy or strange decays. And on the largest scale, cosmology, looking for marks in the ancient light from the Big Bang. It's a search on many fronts. A negative result in one place doesn't kill the idea. It just helps narrow the possibilities. It guides theorists toward the versions of the math that might still fit reality. This back and forth isn't a weakness, it's the engine, the tension between mathematical ambition and experimental rigor. That's what sharpens the ideas. It pushes theorists to refine their models, to find versions with clearer predictions. It pushes experimentalists to build more sensitive machines, to design cleverer tests. The goal is that unambiguous moment, a prediction so precise and an observation so clear that the question is settled. That's the hard, slow work of frontier science. A dialogue between imagination and evidence over generations. The debate itself is a sign of a living field, struggling toward a truth that's just very, very difficult to see. The search for hidden dimensions isn't just a physics question. It shows up somewhere else in information theory. The math of data and the geometry of space seem totally separate. But at a deep level, they're starting to connect. There's a bridge between them, holography, not the credit card kind, a cosmic holography. The idea is that all the information about everything inside a volume of space could be perfectly encoded on its boundary. On its surface, like a soap bubble, the film is two-dimensional, but it contains a three-dimensional volume of air. In a holographic universe, that film could hold a complete description of the inside. Every swirl, every vibration. The physics in the full volume is equivalent to the physics on its lower dimensional surface, and this is a concrete mathematical discovery. The add S/CFT correspondence. It shows a precise duality. A theory of gravity in a higher dimensional space is exactly equivalent to a quantum field theory without gravity, living on its lower dimensional boundary. So our three-dimensional reality with gravity and matter could be a projection, a hologram, generated from information stored on a distant two-dimensional surface. That mirrors the braneworld ideas, our universe as a membrane with its physics encoded on its edge, but it goes further. It ties the geometry of hidden dimensions to the nature of information itself. In this view, spacetime might emerge from quantum entanglement, from the connections between bits of information. The three dimensions we move through could be a convenient illusion. A large-scale structure that arises from a vast, hidden network of quantum data. So the search for extra dimensions is part of a bigger story, a story about what reality is made of. Not just particles or forces, but information, the same fundamental stuff that runs our computers. Could the universe at its core be a kind of computation? A geometric process unfolding from a deeper informational layer. These connections aren't just academic, they're guiding lights. They tell us that when we probe the architecture of space, we're also probing the architecture of knowledge. The rules of computation and the laws of physics may be two sides of the same coin. So the next time you save a file, compressing a three-dimensional image into a two-dimensional code, remember, the universe might be doing something similar. It's storing the data of existence in a place we're only starting to imagine. The equations are abstract, but the feeling they give you is human. People have been imagining unseen worlds long before string theory. H.G. Wells and his time machine. He wasn't just building a vehicle. He was saying time was a dimension you could travel, like space. He took a philosophical idea and made it an adventure. A scientist moving through a fourth dimension, watching civilizations rise and fall. It was a story about progress and consequence, using a hidden dimension as its stage. That impulse to explore the unseen, it kept going, it changed. In art and in film, extra dimensions became more than just plot. They became metaphors. They stood for psychological depth, the layers of a mind. They symbolized spiritual planes, places beyond the physical. They opened doors to other realities, to what might have been. A modern example is Christopher Nolan's Interstellar. It shows a higher dimensional space not as some sterile geometry, but as a library of moments, a place where time is a landscape you can walk across. The protagonist doesn't just see it, he feels it, and he uses it to reach across time to communicate with the past. The science is wrapped in human emotion, love, regret, connection. This cultural reflection matters. It shows the scientific search for hidden dimensions touches something primal, a deep human curiosity about what's beyond what we can perceive. We've always sensed there's more to reality than what we see. Art gives that feeling a language. It provides images, stories, an emotional weight that pure math can't. It translates the awe into something you can feel. When a filmmaker shows a tesseract or a writer describes slipping between worlds, they're doing more than entertaining. They're preparing the imagination, helping us grasp the implications of the search, making the staggering idea that our reality is a shadow, a fragment feel not just possible but compelling. This dialogue between science and art is essential. The equations point the way, but the stories make you want to follow. They remind us that at the heart of this grand, technical pursuit is an old, human question. What else is out there waiting to be found? This dialogue between imagination and evidence, it's building towards something new. We've pushed the limits of what we can see with the current experiments. But the horizon is already shifting. The next leap forward will come from machines we're only now designing, from observatories we'll place beyond Earth itself. So the search for hidden dimensions is moving into a new phase, a phase defined by unprecedented scale and sensitivity. On the ground, physicists are planning colliders of staggering ambition. One concept is the Future Circular Collider. Imagine a new tunnel, not 27 kilometers, but over 90 kilometers in circumference, burrowing deep beneath the European landscape. Its goal would be to smash particles together with energies many times greater than the Large Hadron Collider can achieve. At those incredible energies, the veil between our dimensions and any hidden ones could grow thinner. The probability of creating a microscopic black hole would increase, or seeing a graviton slip away. It would probe distances so small they approach the very scale where extra dimensions might naturally uncurl. Then there's another idea, a muon collider. Muons are heavier cousins of the electron. Because they don't lose as much energy to radiation as protons do, they could deliver cleaner collisions. More focused collisions at the highest energies. This machine would be a precision scalpel, cutting into the fabric of spacetime with a clarity we've never had before. Either of these behemoths would transform the hunt from a search for hints into a direct investigation. They are the microscopes of the future being drafted today. But the frontier isn't confined to tunnels. It's expanding into the silent ocean of space. A mission called the Laser Interferometer Space Antenna LISA is poised to open an entirely new sense. Instead of listening for the high-frequency chirps of stellar mass black holes, like ground-based detectors do, LISA will float in space, forming a triangle of spacecraft millions of kilometers apart. It will sense the low, rumbling gravitational waves from the most colossal events in the universe, the mergers of supermassive black holes at the hearts of galaxies. These waves have been traveling for billions of years, carrying pristine information about gravity in its most extreme form. Any modification to gravity caused by hidden dimensions would subtly alter the shape of these waves. LISA will listen to the symphony of spacetime itself, and in its harmonies we might hear the faint, distinctive note of a higher dimensional geometry. The coming decades promise a powerful synergy. Earth-bound colliders will push the frontiers of the infinitesimally small, recreating the universe's first moments. Space-based observatories will monitor the cosmos's grandest dramas, testing gravity across vast ages and distances. Together, they form a complete picture. A dialogue between the quantum and the cosmic. It's a coordinated assault on the unknown, using every tool we can conceive. The search is far from over. In fact, it's just beginning to see its true scale. The most profound tests don't always need the biggest explosions. Sometimes the answer is in the quietest measurement. Beyond the big rings and the space telescopes, there's another frontier. It's a revolution in sensing. It runs on the strange rules of the quantum world. The goal is to feel gravity's faintest whisper, to catch a tremor in spacetime so small it's hard to believe. And to do that, scientists are using quantum mechanics itself. They're taking its most counterintuitive features and turning them into tools. That's the promise of quantum-enhanced sensing. Think about two particles linked by quantum entanglement. Their fates are tied no matter the distance. Measure one, and you instantly know the state of the other. This spooky connection can be harnessed. By entangling clouds of atoms or tiny oscillators, researchers can build sensors of phenomenal precision. They cancel out the random noise, the constant jitter of the universe, to find the signal underneath. It's like a microphone that can pick out one voice in a roaring stadium. These quantum sensors could measure gravitational fields with a sensitivity thousands of times beyond what we have now. They won't look for new particles. They'll listen for the gentle pull of a hidden mass, or more than that, for a subtle deviation in how that pull changes over a tiny distance, a deviation that could be the fingerprint of a large extra dimension. Its presence felt not in a high-energy crash, but in the serene, precise mapping of a force. This leap goes beyond the lab bench into orbit. Future satellite missions are being designed with this in mind. They'd carry ultra-precise instruments called gravity gradiometers. These devices don't just measure gravity's strength at one point. They measure how it changes from one spot to another, just millimeters apart. They create an exquisitely detailed map of Earth's gravitational field, the kind of map where a hidden chamber underground or a slow shift in tectonic plates shows up as a clear bump or dip. But scientists would be looking for something else, anomalies with no geological explanation, tiny, persistent wrinkles in the gravitational landscape that our current laws can't smooth out. These could be signs of modified gravity, hints that on slightly larger scales, from a few millimeters to a few meters, gravity is behaving differently because it's interacting with a hidden dimension. It would be a whisper from the bulk etched into the gentle curve of spacetime around our own planet. That changes the search. It turns the entire Earth and the space around it into a fundamental physics lab. We're not just building machines to probe reality anymore. We're using reality itself as the detector. Every mountain, every ocean trench becomes part of the experiment. The quiet, relentless work of measuring our world with ever greater fidelity becomes a hunt for cosmic architecture. It's a technological arms race in precision. The prize isn't just a better map, it's a glimpse into the very geometry of existence. The next great discovery might not come from a flash in a collider. It might come from a barely perceptible sigh in the gravity well we call home. The math of hidden dimensions doesn't lead to just one reality. It often points to many. An almost unimaginable number of them. That's the landscape. It comes straight out of the geometry of those curled up Calabi-Yau shapes. Each distinct configuration, each possible twist and tunnel in the six-dimensional manifold that corresponds to a different set of physical laws. A different vacuum state for a universe. The calculations suggest there could be 10 to the 500 stable configurations like that, a number so vast it dwarfs every star we can see. In this view, our universe, with its specific electron mass and gravitational constant, it isn't the only possible outcome. It's just one possible outcome. One bubble in a frothing, eternal cosmic foam. That's the multiverse hypothesis, and it might be the most humbling idea to come from the search for hidden dimensions. It forces a radical shift in what we think physics can do. For centuries, the goal has been to derive the laws of nature from elegant first principles. To find the single, beautiful equation that explains why things are exactly as they are. But if the landscape is real, that goal might be a mirage. There might not be a single, deep reason why the fine structure constant has the value it does. It might simply be that in our particular bubble, in our particular corner of the cosmic landscape, that's the number that came up. The laws we are trying to derive might not be necessary truths. They might be local facts, historical accidents frozen into our pocket of reality when our cosmic bubble inflated and cooled. That doesn't make the search meaningless. It reframes it. Instead of asking why the laws are what they are, we might ask a different question. Why do we find ourselves in a universe that allows for our existence? That's the Anthropic principle. In a near-infinite landscape of possibilities, most universes would be stillborn, too unstable, too hot, or too empty to ever form atoms, stars, or planets. Only a tiny fraction would have the precise, delicate tuning needed for complexity, for life, So it's not surprising that we find ourselves in one of those rare habitable corners. We are here because only such a corner could produce observers to ask the question. The multiverse idea is deeply controversial. Some argue it moves beyond testable science into the realm of metaphysics. If we can never observe these other bubbles, can we truly call it physics? Yet, its proponents argue it is the most natural outcome of the mathematics we already trust. The geometry of extra dimensions doesn't lead to a single answer. It leads to a library of answers, and if that library is real, then every measurement we make, every constant we pin down becomes a clue. Not to the one true law, but to our specific address in a vast and mostly invisible cosmic archipelago. It suggests the hidden dimensions did more than shape our universe. They may have spawned countless others, each with its own unique story, its own unseen geometry forever beyond our horizon. The hardest part here isn't the math. It's the storytelling. How do you make someone feel a dimension they can't see? That's the art of it. You need analogies. The classic one is the ant on a wire. To us, it's a one-dimensional line, but to the ant, the surface of that wire is a two-dimensional landscape. It can go along the length and also around the circumference. That curled-up dimension is a whole new world for something small enough to see it. That image gives a foothold. It makes compactification feel less like an abstract equation, more like a property of scale. Then there are shadows. You shine a light on a three-dimensional object like a spiral spring. Its shadow on the wall is a two-dimensional shape that pulsates and changes. That shadow is a lower-dimensional projection, a more complex reality. It's a direct metaphor. We might be the shadows cast by objects moving in a space with more directions than we can point to. These tools build intuition. They translate an intimidating concept into something you can almost touch. But now the tools are evolving beyond static analogies. Interactive simulations are coming in, virtual reality. Imagine putting on a headset and navigating the inside of a four-dimensional hypercube. Your perspective shifts as you move through a geometry that folds in ways our normal space does not. Or picture manipulating a visualization of a Calabi-Yau manifold, using hand controls to rotate its intricate form. Watching how its complex topology twists and connects. You're not being told about hidden dimensions, you're exploring a model of one. This transforms the subject. From a lecture into a puzzle, an explorable mystery, this work is vital. It's not just about teaching established facts, it's about inspiring the curiosity to tackle the unsolved. By making the intangible tangible, educators do more than explain a theory. They build a bridge. They turn public awe into public understanding, and that understanding sustains support. For a quest that may take generations, it ensures the next great mind to unlock a piece of this puzzle might be a student today, who first encountered the idea not as a wall of equations, but as a world they could step inside and wonder at. The future of this search depends on making the invisible feel real. Confirmation would come quietly, a consensus among experts. The data would line up. The predictions would match, and that would be it. A new chapter begins. At first, there'd be Nobel Prizes, textbooks were written overnight, but the deeper changes, those would come slowly. They'd reshape how we see everything. Technologically, it's a complete mystery. Mastering extra-dimensional physics isn't like inventing the transistor. We wouldn't just get a fifth-dimensional power switch. The scales are unimaginably small. The energies are forbiddingly high, but still understanding a new layer of reality's architecture, that's always come first. Knowing the geometry of the atom gave us nuclear energy, the silicon chip. So comprehending the geometry of spacetime itself, in its full form, that could unlock things we don't even have words for. Insights into gravity, maybe, or materials with properties that defy our logic, or new kinds of computation operating on principles from a higher plane. The potential is vast and it's unknown. Existentially, it's a monumental triumph. For all of human history, our reality was defined by what our bodies could perceive. We built tools to extend our senses, but they always worked within the same dimensional theater. Confirming hidden dimensions is different. It proves definitively that the human mind, through math and experiment, can discover truths that are permanently beyond direct experience. We'd have mapped a territory our bodies can never visit. That expands the very idea of knowledge. It confirms the universe is stranger than we suppose, and that our reason is powerful enough to comprehend that strangeness, even when our senses fail. A discovery like that becomes a cornerstone, a story told for millennia, right alongside the Earth orbiting the Sun or life evolving. It alters our place in the cosmic narrative. We're no longer just inhabitants of a three-dimensional stage. We become its cartographers, and understanding that we live within a shadow, a fragment of a grander geometry, that gives a new kind of humility. And a new kind of grandeur. Our home is smaller and more magnificent than we ever dreamed. The search inside the Large Hadron Collider is about data. A constant flood of it, billions of particles collide every second. Most of those collisions are just background, they're noise, the known physics playing out. The real challenge is finding the one event in a billion that's different, that breaks the rules, so you need a filter. That's the trigger system. It's the first defense against all that data. These aren't simple switches, they're networks of electronics and fast software. They have to decide in less than a microsecond whether a collision looks unusual. Whether to save it. It's a high-stakes filter, saving only the most promising flashes in a constant storm. What are they filtering for? One thing is a graviton-like resonance. In theories with large extra dimensions, a graviton could be produced, or a related particle called a Kaluza-Klein graviton. It would be heavy, unstable, vanishing almost instantly, but its decay would leave a mark. It might split into two high-energy photons, for example, two beams of light shooting out back to back. Their combined energy would stand out from the background, or it might decay into a pair of leptons, electrons or muons, a similar, unmistakable signature. The detectors, ATLAS and CMS, are built to catch these signals. Their layers of sensors work like a three-dimensional camera, capturing the paths and energies of every particle from the chaos. Then algorithms reconstruct what happened. They trace the digital breadcrumbs backward, piecing the story together, looking for that spike in the data. That bump on a graph, the sign of a heavy, fleeting visitor from a higher dimensional theory. So far, the bump hasn't appeared. The searchers have set stricter and stricter limits. They've ruled out entire classes of models where the energy scale of the extra dimensions is too low. This is how science often progresses without a discovery. Not with a loud yes, but with a quiet, persistent no. Each null result is crucial data. It's like a mapmaker shading out a region, telling the theorists this particular version of the idea doesn't match reality. Your mathematical castle can't be built on this ground. That feedback loop is essential. It guides theorists back to their equations, pushing them to refine their models, to propose new, more subtle signatures that might have evaded the earlier searches. The hunt becomes a dialogue, a conversation between imagination and evidence, conducted in petabytes and probability. The LHC, in its silent circuit, embodies that patient, experimental quest. It's a machine built not just for discovery, but for deep listening. And in the silence it has recorded so far, it is already telling us things. Profound things about the shape of what's to come. Gravitational waves are the universe speaking. LIGO and Virgo heard them, and that wasn't just a new window. It was a new sense, a way to feel the cosmos. These aren't light, they're ripples in spacetime itself, stretching and squeezing the distances between atoms as they move through. They come from the most violent things, the final spiral of two black holes, each dozens of times the sun's mass crashing together, or two neutron stars colliding. In those moments, gravity isn't a pull, it's a roaring, dynamic force, and the waves it makes are pristine. They travel for billions of years, barely touching anything. They arrive clean, carrying a perfect record of the extreme physics that made them. That purity makes them more than a tool. They're a direct probe into gravity itself. Into the strong field regime where spacetime is warped almost to breaking. Einstein's theory has very specific predictions for these waves. Their shape, their frequency, how they rise to a crescendo and then fade in a ring down. It's a fingerprint, a signature for the mass and spin of the final object. But what if that fingerprint has extra lines, subtle deviations woven in? This is where the search for hidden dimensions finds an ally. If reality has extra spatial dimensions, then the way spacetime vibrates after a colossal collision could be different. The ring down of the new black hole might have extra tones. Fainter harmonics, or the way the waves dissipate, might not match Einstein perfectly. It would be a tiny whisper inside the larger signal, a hint that spacetime has more room to vibrate than our three-dimensional models allow. Finding that would be monumental. It wouldn't be like spotting a new particle. It would be listening to the geometry of creation and hearing an echo from a higher dimensional space. Gravitational wave astronomy shifts from mapping cataclysms to testing the architecture of reality. Each new detection, especially the heaviest black hole mergers, is another chance to listen. To ask if the universe's deepest vibrations match the song our three-dimensional equations wrote. The future of this listening is promising. Next-generation ground detectors and the space-based LISA will hear these tremors with far greater clarity. They'll catch supermassive black hole mergers, events of unimaginable power. In the clean, complex waveforms of those distant collisions, scientists will search for the faintest traces. A signature written not in light but in the trembling of spacetime. A potential echo from dimensions we've never seen, but that the universe itself might be vibrating into. Gravity's weakness isn't just a curiosity, it's a glaring inconsistency, a problem with the hierarchy. The numbers are staggering. The force that holds an atom together is about 100 trillion times stronger than gravity. That's a 1 with 38 zeros. The difference is so immense it feels less like a law of nature and more like an accident, an unexplained accident. Why should one force be so feeble while the others are so strong? For decades, this has been a deep puzzle. It suggests something's missing, that we're not seeing the full story. And hidden dimensions offer a solution, an elegant one. Think of a powerful speaker in a huge, empty concert hall. The sound waves spread out in all directions, filling the entire volume. If you're standing in one corner, the music sounds distant, faint. The strength of the sound hasn't vanished. It's been diluted, spread across a much larger space. Now imagine our three-dimensional universe is just that corner, and the entire concert hall is the bulk, the higher dimensional space. Gravity isn't confined to our corner like the other forces. It's the only force whose waves can travel into the full volume of the hall. From our perspective, gravity seems weak, but its true, fundamental strength might be just as powerful as the other forces. It's just that most of its influence is leaking away, spreading into dimensions we can't perceive. This transforms the hierarchy problem. It's not a mystery of numbers anymore. It's a question of geometry. The puzzle isn't about why gravity is weak. It's about why our slice of reality is so small. So the search for extra dimensions becomes a direct attempt to answer one of the most fundamental whys in all of science. It's not an abstract exercise, it's a hunt for missing architecture, the architecture that would make our universe's rulebook feel whole, natural, unified. Finding evidence for this dilution would be a monumental shift. It would tell us the force that shapes galaxies and holds planets in orbit is not a feeble whisper. It's a roar echoing in a hidden, grander space. Our theory's real test isn't just explaining what we see, it's what we could do. If we ever confirm hidden dimensions, the question becomes practical. Could we interact with them? Could we build something that uses them? That's the edge of theoretical engineering, where physics meets science fiction dreams. Take the warp drive, not the fictional one, the serious mathematical model from physicist Miguel Alcubierre. It doesn't make a ship go faster. It proposes manipulating space-time geometry. Contract space in front of a vessel, expand it behind, create a wave that carries the ship along while it sits motionless inside a bubble of normal space. This wouldn't break the speed limit for anything inside the bubble, but the bubble itself could, in theory, move faster than light. The catch is immense. It requires matter with negative energy density, something we've never seen. That may not exist in our familiar three-dimensional world, but some brain world models offer a sliver of possibility. In a universe with extra dimensions, the properties of the vacuum could be very different. The exotic matter needed for a warp bubble might not be a forbidden substance. It could be a configuration of fields that reaches into the bulk, a form of engineering that leverages the full, multidimensional geometry of reality. This isn't a blueprint, it's a thought experiment wrapped in advanced mathematics, but its value is profound. Confirming hidden dimensions does more than answer old questions. It opens new chapters in what is physically possible. It shifts concepts like faster than light travel from pure fantasy into extreme theoretical exploration. A civilization that fully understood the architecture of spacetime, including all its hidden rooms, wouldn't just be mapping the cosmos. It might be learning to reshape the very fabric of its journey through it. The distance between that understanding and any practical application is cosmic, spanning centuries or millennia, yet the direction is clear. Every step toward confirming the multidimensional nature of reality is a step toward a future where the universe's deepest secrets are not just observed, but perhaps one distant day invited into the workshop of human ingenuity. But this whole landscape of possible universes, it brings up a question, a pretty unsettling one. If all these configurations are mathematically possible, why are we in this one? The answer might be right here, in us. That's the anthropic principle. It's controversial, but it's a powerful line of reasoning. It just says the universe we see has to be compatible with us being here to see it. We are here asking. So the universe had to have the right properties: stars, planets, chemistry, life. Our existence is a piece of data, a crucial one. With hidden dimensions, this principle becomes a guide. A way through that cosmic landscape, the specific way the extra dimensions curl up, their exact Calabi-Yau shape that sets the laws of physics for that universe. And most of those 10 to the 500 possible shapes, they'd lead to dead universes, universes that expand too fast or where atoms can't hold together. Our forces are too weak to build anything complex. They're stillborn. Our universe, with its 3 stable dimensions and this particular curled-up geometry, is one of the rare ones. A configuration where the numbers work, the strength of gravity, the mass of the electron, the nuclear forces, all tuned within a narrow window, a window that allows for galaxies, for organic molecules, for conscious minds. The anthropic principle says this isn't a miracle, it's a selection effect. In a near-infinite multiverse of possibilities, we could only ever find ourselves in a universe that could produce us. The hidden dimensions are curled up this specific way because any other stable configuration that didn't support observers would just go unobserved. By definition, this idea is deeply controversial. To some scientists, it feels like a retreat, like admitting we can't derive the laws of nature from first principles. That we're resorting to a tautology, we see what we see because we're here to see it. It seems to replace the dream of one elegant equation with a statistical shrug. But its proponents argue it's a necessary shift. When you face a potentially real multiverse, the old question changes. We're not looking for the one necessary set of rules anymore. We're asking why, out of a vast ensemble of real universes, we ended up in this particular one. Our existence becomes the key evidence. It ties the search for the geometry of hidden dimensions to the deepest questions. Life consciousness, it suggests the architecture of reality and the fact of our awareness. They're not separate mysteries, they're parts of the same story. A null result can feel like silence, but in the search for hidden dimensions, that silence is speaking volumes. Every experiment that comes up empty is not a failure. It's a mapmaker shading out a vast territory of what the universe is not. The Large Hadron Collider has not seen microscopic black holes. The tabletop gravity experiments have not found deviations down to a fraction of a millimeter. Our most precise cosmological maps show no glaring anomalies from the early universe. These are not dead ends, they are signposts. They have systematically ruled out whole families of theoretical models. They have pushed the possible energy scale for extra dimensions higher and higher, into realms that challenge even our most ambitious machines. This rigorous process of elimination is the unsung hero of the scientific method. It forces a beautiful discipline. Theorists cannot just dream up any elegant geometry. They must now craft models that survive this gauntlet of negative evidence. The ideas that remain are more subtle, more sophisticated, and more deeply intertwined with other cosmic puzzles. They are the survivors. This teaches a profound lesson about how truth is found. We often picture discovery as a sudden flash, a eureka moment, but more often it is a slow, collective winnowing, a patient narrowing of possibilities through relentless questioning. Each careful experiment, each precise measurement that finds nothing, is a step. It is clearing away the underbrush so that when a signal finally appears, it stands alone. Unmistakable, the path to a paradigm shift is not a straight line to a revelation. It is a spiral of refinement built on a foundation of respected silences. The value of knowing what isn't there is immeasurable. It is the quiet, persistent work that ensures when we finally hear the whisper from a hidden realm, we will know beyond doubt exactly what it is we are hearing. The idea of hidden dimensions gets wrapped up in these stories. You picture a doorway, something you could just walk through into another world. That image is everywhere. But that's not what the science points to. The reality from the equations is much quieter. There are models, braneworld models, that allow for parallel universes. Separate membranes floating in a higher dimensional space, but interaction isn't like opening a door. If another universe is right there on a nearby brane, every bit of it would be invisible to us. Our light wouldn't touch it, our forces wouldn't reach it, we might never even know it was there. The only possible connection would be gravity. Gravity might be the one thing that seeps through. Its faint pull could be the only signal, the only whisper we'd ever get from a neighbor. This isn't about dismissing the stories, it's about two different kinds of truth. Science fiction asks what if in the most dramatic way. Science asks what is. It builds a ladder, one careful rung of evidence at a time. The search for extra dimensions is part of that. The implications are huge, but they show up in the quiet language of math, in the precise click of a detector. A confirmed signal wouldn't be a stargate. It would be us decoding a piece of cosmic architecture. We'd finally understand our reality is just a fragment, a piece of a much larger geometry that manages expectations. Not to limit the awe, but to deepen it, so when a discovery comes, we see it for what it is. Not a portal opening, but a deeper, more hidden layer of existence being unveiled. That ultimate dream is breathtaking. To take the whole messy catalog of the Standard Model, the quarks, the leptons, the photons and gluons, the Higgs, and show it isn't random. That it's the inevitable outcome of geometry, the vibrations of strings constrained by the shape of a Calabi-Yau manifold should produce a specific spectrum. It should give us exactly 3 generations of matter. It should yield the exact gauge symmetries for the electromagnetic force, the weak force, the strong force. The numbers we measure, the masses and coupling constants that seem arbitrary, they'd all come out of the equations, locked in by the topology of the hidden space. That's the promise. It's not about adding new pieces to the puzzle. It's showing the puzzle we already have is the only picture you can make from those hidden dimensional pieces. We'd see the universe couldn't have been any other way. The rules we live by would be revealed not as choices, but as mathematical necessities. A single framework explaining everything from the spin of an electron to the fusion in a star. We're not there yet. The path is littered with challenges. The landscape of possible Calabi-Yau shapes is vast. Each one yields different low-energy physics. Finding the one that matches our world is like searching for a single snowflake in a blizzard that fills the observable universe, but it isn't hopeless. Every negative result from the LHC, every tighter constraint from a tabletop gravity experiment helps. They prune the landscape. They tell theorists which mathematical paths are dead ends. They force new ideas, new mechanisms to select one unique vacuum from the multitude. This work is a grand collaborative dialogue. It spans continents and generations. Thousands of researchers, from pure mathematicians to experimentalists, driven by a shared belief that reality, beneath its complexity, is elegant, that it is mathematical, and that the human mind, through patience and creativity, can comprehend it. The dream of unification is the engine. It's the quiet conviction that keeps them working on problems that may not be solved in their lifetimes. Because the reward isn't just a new particle or a modified equation. It's the moment we look at the universe and finally see it not as a collection of parts, but as a single, necessary whole. We started with a question: what if there's more to reality than what we can see? That question led into some of the deepest mathematics we have, into the geometry of Calabi-Yau manifolds. And it led to building huge machines, rings deep underground where we recreate the universe's first moments, listening for echoes of microscopic black holes. We've turned quiet lab benches into listening posts for gravity's faintest tremors, and we've pointed our most powerful telescopes at the oldest light. Searching for cosmic fossils, every tool we have, pure thought, brute force engineering, all part of one effort to listen, to test, to know. The extra dimensions are still hidden. A possibility just beyond our reach, but the pursuit has changed us. It forced a deeper understanding of gravity's weakness. It reshaped our models of the cosmos's explosive birth. It wove new connections between the fabric of space and the nature of information. We expanded what we consider possible. Science at this frontier isn't just a collection of answers. It's a state of perpetual wonder, a commitment to following the evidence, no matter how strange the path. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That captures this quest. The search for hidden dimensions isn't over. It's an ongoing conversation with the universe, a dialogue written in mathematics. Tested in fire and silence, it continues in the next run of a collider, the next analysis of a gravitational wave, the quiet hum of a quantum sensor yet to be built. And with each step we get closer to a fundamental truth, not just about the cosmos, but about our capacity to seek, to question, to understand.